Hello everybody and welcome back. So it's the end of week 4 now and you guys should be getting pretty good and pretty advanced with your Vex. So hopefully you're understanding the syntax, hopefully you're learning to sort of think in the way that you should in Vex, think logically and be able to kind of communicate with the program and tell it exactly what you want. So we're now going to be talking about a practical example of how to kind of apply not only everything we've learned this week, but this technique will kind of apply everything we've learned up to now, really. So it may be a bit of a challenge, especially anyone who has never coded before. This is one of those lessons where I spoke about where I said that giant chunks of code can be really intimidating. The logical flow of data can be very scary, and even just looking at a giant chunk of text, it just looks, you just think you don't understand. So please, if you are new to it, please do not get intimidated by this. You've been doing well up to this point. Let's just persist. Everything we're doing in today's lesson is something you've already done before. You just need to logically break it down and work through the steps. Okay, I will provide the scene file for you in case you get stuck. I will also be able to help you, and you can help each other as well. But I believe in you. I know you've got this. Okay, so we're gonna basically, I've created a kind of like a rock. Okay, just a basic rock, and I'm essentially just Voronoi fracturing it. So you'll see I've got loads of points. Now, I haven't gone down the whole route of clustering these on purpose because I'm going to be creating, essentially what we're going to be creating today is a tiered constraint network. So we're going to essentially be creating clusters of our own, but they are clusters that are not just rigidly locked together. Instead, it's clusters made up using a constraint network where we have different levels of strengths of constraints. Okay, so we can almost create purposeful weak points in the rock where we would like it to fracture much easier, and then other areas which are kind of maybe more medium, and then another place which will just be very, very strong and will only fracture into these tiny pieces when it gets a massive impact, but nowhere else. So we're going to try and basically be using this to control the way that these things break. And this technique we've used a lot at the studio. This is something that I use all the time. I don't like to just cluster using the Voronoi fracture because you get non-convex shapes, and so then you have to do the convex decomposition. It's a pain. I prefer to just fracture it into small pieces and then use the constraints to essentially control how this thing breaks and how we group those pieces together. Okay. So we've got a basic setup. We're fracturing, unpacking, and I should just point out that I'm not adding any interior detail and things. I'm not going crazy. I've explained before, I'm limited here on a laptop, so I don't want to run any simulation that's so heavy it's going to crash the scene, and then that's going to be a pain for you guys to have to cut while I have to reload my scene. But obviously you would go in and add much more detailed pieces and change the way that you fracture nicely to get a much better result than what I'm getting here. What I want to do is show you the setup of sort of the Vex and how we're going to use that to create this amazing effect, and then you can take it even further. So I'm basically just promoting the name over here after packing, just because it needs to be at point level. Creating a rest and diving inside the DOP, we just see I've got a basic ground plane, loading RBD packed, rigid body solver, some gravity, and then a constraint network. So very, very standard. I haven't changed anything here, but I haven't plugged in the constraints over here. So because I just want to show you. So we've got a basic setup. We've got this rock that smashes into tiny little pieces. Okay. Yes, obviously tiny little, very Voronoi looking pieces. Please go and add interior detail or do something to break that up. But what you're going to see is that this cool method of doing these tiered constraint networks actually means you need to do a lot less work to get this all to look good, because it's not going to fracture this way. It's not going to break into a bunch of tiny pieces like this. Instead, we're going to, let's run through the simulation and show you the kind of result that I'm getting. So even with very low res geometry, with not much interior detail, look at the sort of, this, we get nice sort of broken edge at the bottom here where it impacted. We get all of this breaking away. We get a nice crack right the way up through the rock at sort of very predefined places, and like here, it's cracked but kind of holding together a little bit. So this is something that would happen where we've got these weak sort of points, flaws in the rock that let it kind of crack right the way through, and yet at the actual impact site we get really breaking into lots of tiny pieces. Okay, this is the method we're going to be examining today, and it's relatively light. It just takes a little bit of coding, but because it's all in Vex, it's actually pretty fast to process. Okay, so let's have a look at it. So because of this coming out of a second input, I often put down a null just so that I can view my constraints before I start working with them. So that's why I've got this null over here, because obviously if you click on here, you only see what's coming out of your first output. So anyway, here's our constraint network that's created by the Voronoi fracture node. Okay, and we could, so I'm going to dive inside here and show you, I've got a Voronoi noise in here to create the clusters, but I wanted to show you that this is not my preferred method for creating my larger clusters. The reason for this is that you have to kind of control it using frequency, which, I mean, that's fine. That's not the worst thing, but I prefer direct control over the exact placement of these kind of flawed fracture points and how many large clusters I want. Okay, because we're essentially going to be creating big clusters that then break apart from one another much easier. So in other words, this line is where it's going to break really easy because these two almost want to be separated from one another. And yet the internal constraints are much stronger, so they will only really break at the impact site or if they get hit by something else. Otherwise, this whole blue piece will stay together, this pink piece will stay together. Okay, so this is what we're sort of working towards. But I have no control in here of how many pieces there are. Yeah, sure, I can change my frequency, but then I have to, okay, hang on. I think I've got 4 pieces here, 1, 2, 3, 4, but maybe, I see there's a 5th one on the back. I really don't like to work this way. So I'm going to show you a different method that I use for creating Voronoi. You're welcome to use it, or if you want to, you can skip this whole step and just do it this way. Okay, so then here I'm just using a seed as a random and writing that out. Okay, in this case I'm writing it to color, but you'd write it to a cluster attribute. Okay, so that's up to you. Instead, what I do is so here I'm just deleting all the polylines, keeping just the points. I'm sorting the points randomly, just so that I have control over the seed of these points. And then I'm deleting, but I'm not deleting randomly. I'm not deleting a random number of points. I'm literally deleting all the points that are greater than a certain point number. But because these points are so randomly sorted, it kind of equates to me getting 4 random points, but it's giving me exactly 4 because I say that I want 4 points. If I say 6, I will get exactly 6 every time. So this is a much nicer method for getting exactly the right number of clusters I want. And then to get the same sort of Voronoi shape, wherever we've isolated those points, if we just have our points on our constraints search for the nearest point within this point cloud, then it will give us essentially the same effect as a Voronoi fracture. So hold on, let's try and see why this is not visualizing. Oh, sorry, it was just a viewport glitch. So you see here we've got, in fact, it looks a little bit better than Voronoi because they seem to be a little bit more, round rather than so triangular. And I've got 1, 2, 3, 4 points. I can change the seed if I want different 4, but I know that every single time I'm guaranteed to get exactly 4, no more, no less. And even if you wanted to, instead of being so random like this, if you really needed this to break in exactly a very specific way, then you could go and manually like hand place or hand pick certain points to keep. So let's say you only wanted this edge to break off. You'd put one big point right in the middle here, and then one point on the edge here, or in fact, you'd probably put the two close to one another, and it'll basically create a fracture line between the 2 points. So it gives you a lot more control. So I'm just using a near point here to transfer to find the nearest point, because the nearest point's number, because it's 0 to 3, because there's 4 points, will be my cluster number. So now my cluster numbers will be literally 0 to 3. There we go, 0 to 3. And then I'm also setting a cluster group, but it's cluster underscore and then the number of the cluster. So cluster 0, 1, 2, and 3. Okay, we're using the sprintf function. Now here's where we start getting into the real nitty gritty of it. What I want to do is remove all of the constraints that join these two. So you'll see here some of these constraints go from one cluster to another. Now, and all the constraints are made up of polylines which with only 2 points. Okay, so here there's a polyline with 2 points, and then from that there's another polyline with 2 points. And they're all separate, so that we've got a lot of primitives. They're not one continuous polyline. And essentially, each point has a name attribute, and this polyline is saying, is kind of attaching the two rigid body particles that have that name and that name. In other words, the names that are on the 2 points that this polyline is attached to. Now, what tends to happen when this wants to break, even if we had to go and make all of these joining constraints, which I'm going to call inter constraints, because they're going from one cluster to another, so it's inter-cluster constraints as opposed to inside, which is intra. I hope that's not confusing to you guys, but anyway, so intra is internal and then inter is between. So anyway, even if we made this fracture line weak, with really weak force, you'll often find that it will not break apart. And the reason for that is when it impacts here, a lot of these will break. There will be an impact, will propagate up through these constraints, and it will break a whole lot of these constraints. But if it just happens to need to propagate too far, so like this goes right the way through, you'll find that maybe even if one of the constraints between this and this is unbroken, these pieces will not move at all. Okay, it's not like in real life where if you had glue joining these and then you had to break away all the glue except for one tiny piece, well, now that glue gets weaker because there's only one part of it. It's infinitely strong unless it gets broken by an actual impact force, which means that very often we would come across this problem where we've got these weak constraints and thinking, why is it still not breaking apart? The entire thing just falls like one giant indestructible rock. And constraints are breaking, but just one of them remains, and then, well, it just doesn't fall apart like we expect it to. Okay. So what I want to do is remove all of those inter constraints. So now every constraint is only an intra constraint, basically constraining all the cluster, this cluster to itself, but not joining it to any other pieces, which essentially means that as we would click play now, these 4 pieces would fall apart as though they're not even joined at all, as though we broke them and then stuck it together, but without any glue, just kind of held it together and then let it go. They would fall apart in the air, or as they touched the ground, they would just separate because they're just separate objects. But what we're now going to do is we're going to run through, looping through these clusters and create a single constraint that joins this cluster to this cluster. Not a whole a lot of constraints between every single part, because we don't want to have that thing of like, oh, well, what if one of them doesn't break? Instead, we just find the center point of this cluster, the center point of this, and connect them with one single constraint. That way, if it gets an impact, it will break, or it will not, depending on its strength. And if it breaks, then that entire cluster is separated from this entire cluster. Okay. And we can also then have direct control over how far we search for constraints. So does this blue one, well, in fact, so this yellow one, yes, obviously we want it to connect to the green and blue because they're right next to it, but do we want it to also have a constraint that connects it to the purple? Maybe we do, maybe we don't, but we want to be able to control that. And that in this current state, like here, we just don't have control over that. So now here's what here's where it gets a little bit hairier. So just please stick with me. This is not too bad. Okay. So I'm going to here basically what I'm wanting to do is building up an array of clusters. I know exactly how many clusters I have, but the reason I'm using this unique vals function to check how many unique values I have of the attribute cluster is because what if I do have another, something else in here where maybe I'm fracturing and then I'm deleting a whole chunk of the rock already before the simulation even begins, maybe because you want a nice broken edge. Well, if we do that, maybe we've deleted whole clusters, so then we're wasting time looping over clusters that don't exist. So as a rule, I tend to want to use the code to check how many unique values I have and build up an array and then loop over it instead of just assuming that I have 4. Because right now I know I have 4. But what if I were to turn this whole thing into a procedural system and I'm chucking 5, 10, 15 different rocks in here, and yeah, you want it to all be procedural. So now I've got an array that is 4 in length. I'm creating an empty array of center points, and then on the outside before I enter here, because I want to append to this empty array on every loop. And then inside the loop, I'm looping through my clusters where my value is v and my index is I. And I'm essentially assessing the point bounding box center of that whole cluster. Okay. And then, so I'm using the group in here. That's why we created groups earlier, because this needs a group. Okay. And then I'm finding the center point. So like here I know exactly where the centroid of this is, but the centroid is not a point. The centroid is a location in space. What I want to do is attach, because we need to attach constraints to an actual point number, a specific point that exists, not just some random point in, like some random location in space. Okay. So I'm taking that center location that I found and searching for the nearest point to that center location in order to find that center point. And then I'm appending it to our centers array. So at the end of this, we should have 4 point numbers in this centers array. Now here I'm creating a string group. And the reason for this is because when we loop through and want to basically build, where is it again here? Searching for our nearby points to kind of attach them to one another. I only want to do it within this this group. And in this particular function, it doesn't let you just feed it any other group. It must be an actual string group in here. Okay, so so it's in the format of a string. It's not, you're not referring to a group as we do over here. So as a way around that, I'm sort of building up. So we're going to use some of our string expressions to kind of alter this string. So it's a string separated list basically of which points we're going to be running on. Okay, this is an array of actual point numbers. These are integers. We needed to convert it to the form of a string. So we're going to for each through our center points. Okay, with v now being the the value of that center point. So in other words, its point number. So we're appending it to a group called centers, and in fact, I can't even remember. I think this is redundant, this step. I don't think I ended up using this later, but often I'll create groups like this just in case. And then if I'm not using it later, you can always come and disable it, but it's good to set that up because often you're going to use this. But anyway, what I'm doing is I'm appending to our empty string, I'm appending the name, well, a string version of the point number. So essentially at the end of it, I end up with a string that would look something like this. Something like that, which is like a string that is a space-separated list of point numbers that we want to run over. And again, I say it is a bit weird that we have to do it that way, but that's because this near points function, that's how this array, this argument works. It will not accept an actual group name like this. Look, you tell it, go look at centers, the centers group. Instead, it specifically wants a string with a space-separated string. So we have to build it this way. A little bit annoying, but okay. So we have to first loop through centers creating that group because we need to complete the building of that group before we apply it. So we're looping again. We're doing another for each loop, but we're looping over the center points again, but this time we have our completed list. And then, okay, I'm going to ignore this step for a second. I'm going to come back to this section just now. But once we enter this, what we're doing is we're gathering an array of near points. Okay, so we're looking through every single center point. We're taking that center point and looping through all of the nearby points. But we do not want to loop through every point that exists in this whole piece of geometry. Instead, we want to just isolate those 4 center points. So when we're running this near points function, we're wanting to essentially just look at 4 points, ourself and the 3 neighbors that exist in this entire center point group, which is what we were creating here. So we're running this near points on ourself, on 0, but through that space-separated string group, and then searching for so within a certain radius over here, okay, and then and obviously to ourself, our own v, so our own point number from that point, the nearest points, okay. So we find our near neighbors, but this would include ourself as well. That's why we're going to come back to this section just now. So I hope you guys will follow the logic here. So once we've got this array of points, so this point over here has an array that's filled with this, this, and this, as long as all 3 of those fall within this radius that we're setting here, okay? Then we're going to loop through all of those points, so 3 times. In fact, if we don't exclude ourselves, then we'll loop 4 times. And within this loop, we are creating a primitive. So we're adding a primitive and attaching it between v and v2. Now you'll see here inside of this, our value is v, inside of here it's v2. The reason is because we can't override v like we did here, because we're inside of this loop, which means that v is still a valid variable. We can't override it. So we need to have a v2 because we're inside of a for loop inside of a for loop. Okay. And we're wanting to check essentially ourself, which is v, and v2, which is our neighbors, and build a polyline between those. And then we're just creating a rest length attribute for it. So there you can see I'm creating rest length, which is I'm just measuring the distance between those 2 points. And the rest length is vital for constraints to work properly. And then I'm creating a primitive group called inter, as opposed to intra, which are these constraints are intra, and then the ones that go between them are inter constraints. Okay, so that's quite simple. But the problem with this section is that, first of all, we would be looping over ourself. So we'd actually be trying to create a polyline between ourself and ourself. So as a zero length polyline. And another problem is that, so let's call this, so let's say we loop over this green point first. Okay, so this green cluster. So the green cluster is going to create a constraint that goes from green to purple, green to blue, green to yellow. Then when we go to the purple one's going to create a constraint between purple and blue, purple and yellow, and purple and green, which is incorrect. We do not want two overlapping polygons here that connect these two, right? Same thing, it's going to get even worse when we go to blue, because now blue is going to go blue yellow, blue green, which already existed, so why is it creating a new one? Then blue purple, which why is it creating a new one? By the time we get to the last one, we're just creating redundant overlapping constraints. So because we're assessing our string group, what we should do on every iteration as we loop through is just remove ourself from the string group, because once green has created constraints between itself and all the neighbors, then none of its neighbors should be allowed to create a constraint from itself to the green, because it has already done the work for them. So when we go to green, remove green from the list, then loop over just these three, which then fixes the problem of not looping over ourselves and creating a zero length constraint from green to green, because we've already removed ourselves from the list. So this will then, even on the first loop, we had 4 point numbers in this group, but already as we enter here, immediately we remove ourselves. So this is now 3 point numbers in length. We loop over the 3 points. The second time we enter and we go, let's say on the purple one, it removes itself from the list. Green is already not in the list, so it only looks at blue and yellow. And when we go to blue, it only looks at yellow. And then when we get to yellow, it does nothing. It just doesn't loop at all because it is 0 in length. Now you'll see here I've had to build in an if. So if the length of the string group is greater than 0, so that when we hit that yellow point, we don't even waste time trying to loop over something that's 0 in length. We just exit the loop straight away. But I'm using our regex and just literally creating a regex from sprintf. I'm just literally searching for the point number followed by a space, and then inserting obviously ourself as that point number. Okay, and then I'm doing a replace, and I'm replacing that regex. Remember, we did regex this week, so I hope you guys remember this, and replacing it with nothing. This is our way of removing ourself from that string group list, then looping over only our neighbors, and our neighbors are never allowed to consider us as constraints and constraint targets either, because we've already done the constraints for them. Okay, I hope you guys are following. This is very detailed, but it is actually quite simple and quite logical. If you're not following, please listen to the video again and try to go through it one step at a time. Right. So at the end of this, when I isolate, and by the way, I always use this kind of, it almost looks like an eye, and I make it green for things that are visualizers. So this is not meant to be something that I ever actually use. This is just to check things. In case you ever, whenever you open my scenes, you'll see that there's all these green eyeballs. It's because this is a way of visualizing something. So anyway, when I look at my centers, you see what has been formed is this, actually looks like a constellation, like one of those. Anyway, so these are the connections that it created. So remember, it was green to purple, purple to blue, blue to green, blue to yellow. It didn't create a yellow to green because this radius is not high enough, but you'll see there as I increase the radius, then it goes yellow to green and yellow to purple. But at the most, it's going to do that. So no matter how high I take this radius, it is only looping that many times. And the intergroup, so you'll see here, has 6 primitives only. Okay, so this is working exactly as expected. And I wouldn't recommend connecting everything that's really far away. I'd actually, based on the size of it, I'd find the right size. So you almost want this kind of line. In fact, maybe even less. I don't know. It's up to you how you structure these. Now, we're only isolating it here to visualize it, but here we're keeping it. So actually, although it's a little hard to see, but between these clusters we have this single connecting line, and that is in its own group as well. So now all we do is we use it. In a wrangle, we're just setting strength to be equal to a certain amount. So this is your intra strength, so the strength of all of these lines. But then we're saying if the primitive is inside of the inter group, then give it a different strength, and you're referencing this. So all of these small lines will have a strength of 10,000. Our inter lines will have a strength of 1. So they're very likely to break. You could obviously go in hand, it doesn't always have to be one single value. You could maybe put a noise or apply a random between two different ranges, or you can do whatever you want. But in this case, it was enough for me to just have two different strengths. Then I'm initializing my constraint attributes and jumping into the exact same network. Okay, let's have a look at the results. So you see there, these broke. In fact, let me, at this exact frame, I'm going to dive inside here to show you the constraints. So you can see which ones at the bottom here. You can see these ones have all broken. And you'll see that the inter constraints have broken away as well. Okay, if we middle click, you'll see that there are no there's no inter group anymore, because they have all broken, because they are out of a strength of 1. Okay, so if we jump into it on the first frame, they're there, and then they break later on. Okay, so very, very cool. I would highly recommend this method. It has worked really well for me in the past. This is basically how we do all of our fracturing now. Because you want control over where things should break, and there are other methods for that, but this is one of the best. And then it also gives you really nice looking clusters, because instead of letting this cluster for you, what you can do is fracture this much smaller, like really, really tiny pieces, and then your intra constraints. So like these, with the yellow, it would be much smaller, so you'd have this little cluster, and you'd make the strength -1, so it's infinitely strong. It will never break. So you're not intending for that to break, but you're using constraints as a way of holding together a much more complex shape. But that shape already has convex decomposition, because each point within that, each primitive inside of that cluster is already a convex shape, because it's been Voronoi. Okay, because Voronoi shapes are always convex. Okay, so it's my preferred method, and honestly, it works really well. So now let's talk about what I want you guys to do. So first step obviously is to just rebuild the system. I know it's probably going to be quite difficult. I hope that this video has explained it a lot more to you, especially this section. You can obviously have access to this file and use it as a reference, or just use it straight away, but you're not going to learn this unless you try and type it yourself. So please, please, please rebuild this yourself, but just use mine as a reference, or the video. Try to understand the logic of what you're doing rather than just copying it line for line. If you don't understand what something's doing, rather research it. Hit F1 on these, figure out what this is doing, go back to the previous week, because as we move forward in this course, we're getting more and more advanced. So if you're not following this right now, then you're not going to be able to follow the final example that we work on at the end of the course. Okay, but I believe in you guys. You can do it, and this is actually really easy. It's just simple logic. Okay, so Step 1, rebuild this and make sure that it's all working. But step 2, and this is going to be a bit tricky, but I really want you guys to do this as a test. Even if you really are lost, just try it. Just, I really, really want you to try this because it's going to push you to learn more about Vex. I want you to take this one tier deeper. So you see how we have these small constraints, also these intra constraints, and then one set of inter constraints. Well, instead, what I'd like you to do is fracture this green cluster, for example. So each of them, but within this green cluster, it should be made up of smaller clusters, which are made up of these, intra lines. So it's like that section would be one cluster, and that section would be another cluster, and that section would be another cluster, and they all form this giant green cluster. But each one of those clusters, you need to go and delete the points, the constraints that go between them, and then loop through and rebuild constraints, just like we did right now with those large ones, but you rebuild them between these small clusters. So then you'll essentially have large clusters, small clusters, and then individual pieces, all connected by a tiered network of constraints. The result of that will be that at the end, we'll have 3 strength values, and you'll be able to even greater control how this breaks. You have very weak, large fracture lines, then kind of medium strength, small lines, and then really strong intra lines. Okay. So that is going to give you fantastic results. You can even go further if you wanted to do 3, 4, 5 subcategories or subclusterings, but normally you don't need that. Like, honestly, in my experience, we've never used more than 2, but we do always use 2. So this, where we just have the one group of clustering, is not enough. You'll get okay results, but really, if you want that realism when it fractures, you really want it to be fracturing in kind of large but weak constraints, small but medium, and then tiny constraints like this, which are either infinitely strong to give you certain cluster shapes or just very strong. So at the impact site, it will shatter into tiny pieces, but then later on where it breaks, you'll have just a chunk will break off, but you won't have the tiny little pieces or shards coming off. So it just helps towards realism. Okay, so I hope you guys are able to manage that. Just a couple of hints towards doing that when you are going to do it. You can just duplicate this setup over here where you're isolating 4 points, but instead maybe make 20 points or something and plug it in to the extra input over here. And then instead of having cluster, you're going to want to label it cluster large and cluster small. And you're going to want to do that everywhere. You're going to sort of create your groups will be cluster large and cluster small. You don't want to just override it. You want to keep them separate. And my recommendation is that because there are a lot of ways to do this, but what you would do is you first actually isolate your small cluster groups. Okay. So you'd run the same kind of setup, but not on the large ones. You'd run this exact same code, but on the small ones. And then when you've built up this network of small constraints, so let's say this was 20. So you've built up this kind of small constraint network. Then I'd run this same setup, but not on the whole thing, just literally on these constraints. I'd run this exact same setup. So this whole section here where you're deleting the connecting lines, but based on your cluster large attribute. And then you run this exact same code, but on the large one on those, and then merge it all together. So you're it's like you're taking your intra constraints and creating your small constraints. And then you're taking your small constraints and breaking them into large constraints. And then merging it all together. So at the end, you're going to have clusters like this, and like small clusters, but then this entire thing will be grouped into one large cluster and connected with one big line. Okay, so then maybe that will be connected to this thing in the middle, and then there. So you'll have like 3 big ones, 20 small ones, and then loads of tiny ones. Okay, so I hope that helps, and I hope that you guys find it challenging, but not impossible. Okay, don't forget, you can ask questions, go through this help file. In fact, I have already prepared a help file which has exactly what I've just assigned you in it. So I am willing to give that to you guys, but maybe only, you know, next week or the one after, you know, if everyone's struggling. I don't want to just give you the answer. I'm basically going to hold on to that help file, that HIP file, until you give this a go. I want to see you trying it, and then I'll give you the answer. Okay, so good luck, and believe in yourself. Don't worry, it is not that difficult. Okay, and I'll see you guys in the next lesson in the next week.